Hey everyone, and welcome back to PrepFusion. So today we'll be starting the lecture 4A of controllers and compensators. So we have learned all the concepts required for solving gate quotients of controllers and compensators. So in this lecture I will do few gate quotients. This is the part A, and in the next part I will do few assignment questions which are not from the gate. So yeah, this is a gate 2007 question where they have told that the open loop transfer function of a plant g of s is 1 upon s square minus 1. If the plant is operated in a unity feedback configuration, then the lead compensator that can stabilize this control system. So basically you have to find the lead compensator that can stabilize this. So yeah, lead compensator can stabilize the system, I told you previously, right? Because it acts like a PD controller, and derivative controller stabilizes the system. Integral controller reduces the steady state error, but it can destabilize the system also because the type was increased in the PI controller or in the lag controller. So lag controller behaves like a PI controller, and lead controller behaves like a PD controller. So I can write like in the this summary section, forgot to write this, that my lag controller behaves like a PI controller. Sorry, lag compensator. I mean, so not controller, lag compensator. Lead compensator behaves like a PD controller. Okay, because its characteristics is like that. So these are the like few things that I wanted to tell. So let's start with this question. So here they are talking about making the stabilizing the system. So system is currently unstable because if you write the closed loop transfer function of a unity feedback, what will happen? It will be 1 by s square. So 1 by s square is obviously unstable because we have two poles at the origin, unstable, right? So now how to solve this? First we need lead compensator. So is this a lead compensator? No, I told you, right? We use compensator with passive elements, and here I have a 0 at the right hand side. This is not a minimum phase system, obviously. So hence this one we can automatically reject by just seeing the options. And here, is this a lead compensator? Again, this is not a lead compensator, this is a lag compensator. Here the pole the pole is more nearer to the origin than the 0. So obviously this also I can simply eliminate. Okay, now this here, is this a lead compensator? Yes, this is a lead compensator, this is a lead compensator, and this is also a lead compensator. Now which one to choose? So for this, what you can do, you can check, because this is a second order system. So this is a second order system, and if I multiply these things, order will increase by 1, so it will become a third order system. So we can use that trick for checking the stability, the Routh array trick, that is the internal product should be greater than the external product for my system to be stable. So here I can simply, for C option, I can simply use the characteristic equation 1 plus g of s into gc of s, because the controller will be directly connected at the OLTF, okay, with the OLTF basically should be equal to 0. So yeah, let me write the characteristic equation. So for C, what will happen? This will be 1 plus 1 by s square minus 1 into s plus 10 into s plus 2, and also 10 is there. Also 10 is there. Okay, so this is equal to 0. this equals 0. Now what else we will do? So obviously we can simply cross multiply. So this one will become s square into s, so I will multiply s cube plus 10s square minus s minus 10 plus 10s plus 20 equals to 0. S cube plus 10s plus 9 plus 10 equals to 0. So now we can check the condition internal product and external product. So here we see the internal product is 90. Okay, IP should be greater than EP. Internal product is 90 and external product is 10 only, 10 times 1. So hence this condition is satisfying. Hence what we can say, system is stable, system stable. Okay, hence option will be C. Okay, but still let's check for the this D option. Let's check for this the D option. So we check for this D option, what will happen. So D option, use the same thing only. This will be 2 times s plus 2, s plus 2 and s plus 10. So in this case what we are observing is like the location of zeros and poles are same, but if I change the controller gain, then also things can happen. Okay, then also it can make it cannot stabilize the system. Okay, that is also important. The controller gain is also an important parameter here. So 2 into s plus 1, s square minus 1 into s plus 10 equals to 0. Okay, so this one will become s square s cube plus 10 s square minus s minus 10 plus 2s plus 4 equals to 0. So this one will become s cube plus 10s square plus s and minus 6. So here the one number itself is negative, so obviously this can't make the system stable. Okay, this is less than 0. Okay, and all the coefficients of s, here the coefficient of s to the power 0 is less than 0, hence not stable, hence not stable. So this is not stable. So this is one thing. So this is how you can check. Or other way what you can do is you can simply use this, that 1 plus kc into s plus alpha by s plus beta into s square minus 1. Now you put this condition and then you put this in the Routh array, and from there you will find the relation between k, alpha, beta, all these things. But this will be very complicated. Obviously you won't be able to solve this because you will need other things as well, that the performance parameter, that like the settling time should be this or this should be that. You need few other information to totally exactly get the values of kc, alpha, beta. So kc, alpha, beta will be in some relation and you have to use that relation here. Whichever option satisfies that relation will be the answer. So in our case C option will satisfy that relation. Okay, so yeah, that will be the fourth question. Now let's go to the fifth question. So in the fifth question they have told that the transfer function of a compensator is given as s plus a by s plus b. Okay, it is a simple compensator whose transfer function is s plus a by s plus b. Now they have told that this gc of s is a lead compensator if, so gc of s is a lead compensator if it is a zero dominating system. So in a hurry what you will do, you will see, yeah, my pole should lie on the left hand side and the 0 should be here. So here the pole is where the pole here is 1 2, so this is 0, this is pole, this is 0 pole, 0 pole. So okay, I was talking about this one because here in a hurry what students can make a mistake is this is a negative sign, yeah, pole should lie on the left hand side, so they will directly click this, they will directly tick this. But obviously a and b are not the poles, minus a and minus b are the poles. If you look at, but not the poles, I mean the roots. Okay, minus a is the 0 and minus b is a 0 pole. So yeah, you just don't take this negative in a hurry, because these are not the zeros and poles, these are a and b. Okay, these are not the roots of this. I mean, these, like, this isn't the zero and this isn't the pole. So the 0 is minus a. So if I do minus a, then this is 0, which is minus 1 for the first option, which is okay, which is in the left hand side. That is fine. So don't be in a hurry and don't tick mark C. Okay, don't tick mark C. Now this is a lead compensator, so obviously it will be a zero dominating system. So if it is a zero dominating system, obviously 0 will lie more near to the origin. So this is a zero dominating system. This is not. This is not. So yeah, this will be the answer. Like, it's very simple. Like, we can just see the question and we can directly animate this. No need to see anything else. No need to see anything else. Okay. So then here, what is this asking? The phase of the above lead compensator is maximum at. So it is not talking about the phase. It is talking about the frequency. So they should have also mentioned frequency, but in with the units you can understand they are talking about the frequency itself and not the phase. The phase of the above lead compensator will be maximum. So when it becomes maximum, it is the geometric mean of the two roots. Okay, two roots or geometric mean of the 0 and the pole. Like that also you can remember. So phase is maximum when the geometric mean. So omega m will be under root AB. So omega m is under root AB, then what is this? So basically it will be 1 times 2. 1 times 2. Because this is the option, so under root AB is 1 times 2, which is equals to under root 2, which is equals to 1.414, or they have directly given the under root 2 option. So obviously A will be the option. Okay, so these things obviously you have to like remember. No, don't have any choice, because this formula you can remember, I hope. Okay, because for the lag compensator and lead compensator, this maximum frequency is same, the maximum phase angle is also same. There the beta changes, the alpha changes to beta, but the formula is same. If you interchange alpha and beta, okay, formula is same. So these formula you have to remember. These two are very, very important formula, you have to remember anyhow. So you can write this in short notes or anywhere. Okay, so yeah, this is the thing. Now the sixth question. So a unity feedback closed loop system has a planned with the transfer function g of s. Okay, unity feedback closed loop system has a planned transfer function g of s and a controller gc of s in the feed forward path. So with it in the feed forward path, it has a controller also. For a unit step, the transfer function of the controller that gives minimum steady state error. Okay, so which what reduces the steady state error? If you recall correctly, if you increase the type of the system, then that will reduce the steady state error. So here, which of the following options increases the type of the system? If I see, only option D increases the type of the system. Now this is a lag compensator, so this will also reduce the steady state error. And what is this? If I say this is not a lag compensator, this is a lead lag compensator. Okay, so anyways these two options are gone, because this is a lead compensator and this is a lead lag compensator. So these two options are anyways gone. Only, like, if you are confused, you may be confused with this too, because this is a lag compensator and this is a like PI controller. So PI controller, here what do I see? I see type increases. Okay, hence obviously this will reduce the reduce the state error. So reduce the state error. Okay, this will also reduce the steady state error, but this will reduce it to a greater extent. Okay, that is very important. So the transfer function to the controller that gives minimum steady state error. Okay, so like, if you want to solve it now, if you are confused between A and C, if you want to solve it, so how do you solve it? So basically, for a unit step input, now this is a simple unity feedback control system. Okay, negative feedback control system. So if you remember the formula, very good. If you don't remember the formula, then you can again derive from basics. So like, it will be something like this. If you recall correctly, it will be R of s minus C of s equals to my error, and my steady state will be s, like final value theorem, limit s tends to 0, s R of s 1 minus t of s, like r of s I take it common, then I can write s into 1 over s. So basically it is a step input, right? This it is a unit step input. 1 over s into 1 minus g of s by 1 plus g of s. So again this g of s will go away. Okay, so only 1 by 1 plus g. So this g, right, this g is actually no, this is not only g, because here we have gc of s also. So don't forget to write the gc of s. Okay, so gc of s is this, so it will be simply g of s into gc of s. So now what you do, now you make s equals to 0. Now you make s equals to 0, so you have to make this s equals to 0, right? So for the first case, for the what is this, for the b case, basically e steady state limit as s tends to 0, so we have to make this 0, right? So what is my multiplication of g into gc of s? So g of s into gc of s for the b case is what, is simply 1 upon s square plus 2s plus 2 into s plus 2 into s plus 1, s plus 2 into s plus 1. Okay, so this lag compensator. So what if I make this one equals to 0, what will this become? This one will become 2 like 1 upon 2 into 2 upon 1, so this one will become 1. So I should write this here actually, limit as s tends to as s tends to 0. So this is 1, so my steady state will be 1 upon 1 plus 1 equals to 0.5. Okay, for the b option. Now let's, obviously for the d option, the type has increased, so obviously it will make it totally 0. So for a d option, the type has increased, so it will make it totally 0. So basically it will be g of s so here this will be 1 upon s square plus 2s plus 2 into s plus 2, not s plus 2, sorry, this will be 1 by 2 plus s plus 3s. Okay, so it will be 1 plus 2 by s plus 3s. Now can we put 0 over here? We can't put 0 over here. Even if we take few things in common, s tends to 0, it will be simply s plus 2 plus 3s square divided by s into s square plus 2s plus 2. Okay, now like we can't put 0, because if I put 0, this will go to blow towards infinity. Okay, so what I will do, I will put this in this equation and I will see. So in the steady state error equation, it it will be like 1 by 1 plus g of s. So if I multiply both of them, so it will become 2s plus 2 divided by s into s square plus 2s plus 2 plus s plus 2 plus 3s square. Now can I put 0 over here? S equals 0. Yes, I can put. This is fine because this will be like this will be 0, but this will be 2. Okay, so 0 plus 2 is fine, 2, and this will be totally 0. So numerator there is 0 and denominator there is 2. That is fine. 0 upon 2 is 2, 0 itself. So this totally makes my steady state error 0. Okay, like that also you can, like from here you can totally see mathematically I have proven it to you, the steady state error goes to 0. Or like you can directly tick mark this because the type of the system increases. So if the type of the system increases, then obviously my steady state error will be go to 0. So for the controller chapter, controller compensator, options become a very important factor. Okay, and to understand what does a lead compensator do, what does a lag compensator do, that is also very important. Okay, then obviously a few questions may come up that you have to reduce the settling time. I will do the assignment questions, and from there you will understand. Okay, few things, so that we will do. So this is the next question. So in this question, what is they are asking is, for the following feedback system, g of s is given. Okay, it is 1 upon s plus 1 into s plus 2. The 2% settling time of the step response is required to be less than 2 seconds. Okay, so the 2% settling time of the step response is required to be less than 2 seconds. So that is one important thing they have told us. Now which one of the following compensators c of s achieves this? So out of all these 4, which will achieve this compensation, right? Which one of the c of s will achieve this? Okay, so basically what you can, like, you can obviously check for each of this. Okay, find the zeta omega n, and from there use the settling time formula. So what is the settling time formula? T settling is 4 by zeta omega n. Okay, t settling is 4 by zeta omega n. So it is 4 by zeta omega n. That is one thing you can do. And next what you can do is this, right? Eliminate from the options. So first, is it a compensator? No, this is not a compensator. Is this a controller? This is not looking like a controller either. Okay, so yeah, we can't do anything. So this is more or less like a lag compensator, what you can say, because like for a lag compensator we have a pole, but the zero is lying at infinity. Okay, there isn't any zero over here, no zero. So we can say it's lying at infinity, or it doesn't exist. So this is like a lag compensator. Anyways, lag compensator can't change the performance parameter, dynamic behavior of the system. Lag compensator on mainly helps in the steady state behavior. So again from here this is a PI controller. PI controller will not be able to help for the dynamic behavior, changing the dynamic behavior. This is a PT controller. Yes, this can help for changing the dynamic behavior. Now this D, this is what, s plus 3 by s plus 3. This is a lag compensator. This is a pole dominating system, so this is a lag compensator. So if this is a lag compensator, then obviously this won't be able to help in the reduction in settling time. We'll see that. Okay, so A option gone, B option gone, only C option is left. So obviously the answer will be C. Okay, so like this you can do in the gate examination if you are very confident. If you are like, no, I am still I'm still confused, what you can do is, you can mark for review. And check the settling time only for this, and see if the settling time is less than 2 seconds. Okay, less than 2 seconds. So if this satisfies, then obviously you can take this, because during 2014 there weren't any MSQ. So if there was MSQ, then I had to check all of this. That would have been a difficult task. Okay, so yeah, so let's first check each option one by one. I have told you that C will be the answer. Okay, but logically I have told you, like intuitively. Now let's solve it mathematically, prove it. So here for A option, okay, for A option, my total G of S into C of S will become 1 by S square plus 3S plus 2. Okay, into this 3 by S plus 5, S plus 5. Then this will be simply So like what will be my closed loop characteristics equation? It will be simply s square plus 3s plus 2 into s plus 5 plus 3 equals to 0. Okay, plus 3 equals to 0. Now this will be simply s cube plus 5s square plus 3s square plus 15s plus 10 and plus 3 equals to 0. Okay, so this will be s cube plus 8s square plus 15s plus 13 equals to 0. Okay, so this basically becomes a third order system. So like how to solve this? So what you can do is you can plot the root locus for this. So like okay, I did one thing wrong. I should have plotted the root locus for this. So basically if I plot the root locus, we have 1, 2 and 5. So pole at -1, pole at -2 and pole at -5. Okay, so now basically what will happen, these two will collide, and here like this is a valid valid location for root locus because I have odd number of poles here. So this is also a valid location, and here I will have a virtual 0. Okay, and where will the other three virtual zeros lie? So I have like here z star or virtual 0 equals to 3, number of poles equals to 3. Okay, number of zeros is like 0 is 0 anyway, that this is a virtual 0. So how many asymptotes I will have? Angle of asymptotes will be minus 180 divided by p minus z, which is 3 into 2n plus 1, where n is varying from 0 to p minus z minus 1. For our case it is 2. So for n equals to 0 it is minus 60. Then for n equals to 1 it is minus 60 into 3 minus 180, and for n equals to 2 it is 5 into 60, which is, it is minus 300, sorry, minus 300 degrees. Okay, so this is minus 300 degrees. So basically 1 will be minus 180, 1 will be minus 60. Minus 60 is something around this area, so obviously it will go here, and minus 300 will be something like this, minus 300 will be something like this, so it will go something like this. Okay, so from here what I can see is with like addition of this pole, this is anyways getting neglected, this is anyways not dominant, and I'm moving more close towards origin. If I'm moving more closer towards origin, what will happen? My this zeta omega n will reduce. Now if zeta omega n reduces, what will happen? My t settling time will increase, because this is anyways non-dominant portion. I can ignore this non-dominant portion. I'm just telling you how to like analyze this, okay, further, because anyways we know that the derivative action will only help us improve the settling time. It will increase the bandwidth, it will reduce the settling time, it will reduce the rise time, all those things, right? So that we know, yes, but to further analyze, this will help you clear your concept also, recall few things. Like this is how you solve questions, like root locus concept is getting used, other concepts are getting used, right? So very important, dominant concept is getting used, so all of them are getting used in this controller and compensator chapter. So that's why it is very important for interview purpose. So obviously for exam purpose you only use that concept, but that is what I wanted to tell you. So zeta is reducing, zeta omega is reducing, hence my settling time will increase, t settling will increase. Okay, so obviously this is not helpful, okay. So I'm just going with a root locus route, okay, to explain it to you. So currently what is my settling time, I don't know. Okay, it is somewhere between these two, okay. So if it is somewhere between these two, obviously it has to be like at minimum, what I can say, I can say it is like between 2. At maximum I can say zeta omega n is 2, so 1 by zeta omega n 2, 1 by 2 into 4, it is 2 seconds only. So at max it can go to 2 seconds, but it will only be more than that, because zeta omega n will always be less than -2. Okay, so zeta omega n will always be less than -2, or like, sorry, yeah, minus zeta omega n will be less than -2, so zeta omega n will be less than 2. So if I take the inverse of this, then 0.5 is less than 1 by greater zeta omega n, so 1 by zeta omega n will be greater than this. And now if I multiply this with 4, so this will become T settling will be greater than T settling will be greater than 2 seconds. Okay, so always it will be greater than 2 seconds. It can be never be 0 than. This is the like at max this can be this. So that's why like from here it is proved. So not possible for us to make T settling less than 2. So we have derived this. So yeah, this is how you do this. Then let's go to the B option. So like B option is very simple. B option is not even possible. Okay, so we'll ignore that option. Now let's go for this C option. So let's see the C option. What does C option do? So if I do this, like B option, why I am ignoring, because it is just a simple integral control. It will not affect the time domain parameters. Okay, so let's go for the D option. So C option is the answer, I know, but first let's check the D option. So again, D option, what it does, it again we have to solve with the concept of root locus only. So because solving with direct equations will be difficult, we have to use the dominant pole concept. Sigma j omega. Now here I have a 0 at s equals to 8 and pole at s equals to 3, and this is 1 2, so this will be 1 2 3 and 0. So -1 -2 -3 -8. Okay, so basically what I can say is like these two will join together and break away, and this will be here. So what will be my angle of asymptote this time? So I have one like 3 poles again. Z is 1, so Z star is 2. It will be 90 and -270. If you like do perfectly, my angle of asymptotes will be -180 divided by P minus Z, which is 2 into 2n plus 1, where n will vary from 0 1 and yeah until 0 1. So basically it will be -90 and -270. Okay, so now obviously this will break away like this. Come over here, and this will be something like, I am not drawing the exact thing. Okay, I'm just drawing it of approximation. So obviously its centroid will be the main thing. So what is a centroid? So its centroid sigma c will be, so what is the compensator actually? Yeah, it is 4, right? K is 4 in our case. Like K is this 4. Okay, this is 1 only, so K is 4. So sigma c is, so this is also another branch, the third branch. So this is a valid point, right? Because I have a 3 roots on the right hand side. So all these are valid points. So sigma c is what? anyways, I will explain you that I don't need to do all this. So with the help of only this, I can understand that yes, this will again be like settling time can't be less than 2 seconds. Only through this I can understand. Okay, so sigma c is summation of poles, which is minus 3 minus 2 minus 1, and minus the summation of zeros, minus 8 divided by poles minus zeros. Okay, so it is 8 minus 6, 2 by 2, which is 1. So around 1 it will, yeah, it will die out. Okay, so around 1 it will die out. So if dies out around minus 1, so this is actually minus 1 or 1. Just hold on a second. Minus 6, okay, pole minus 0. Okay, it will die out around plus 1 actually, not minus 1. So this is, yeah, the poles and number of zeros. So yeah, this will be like something like this actually. So it will actually cross the this axis. So anyways, it will become unstable. Okay, up until this point. So anyways, what we can see is our zeta omega n is again reducing as it is moving towards the right hand side. So zeta omega n is reducing. So settling time 1 by zeta omega n will increase. So settling time will also increase. So here zeta omega n is reducing, hence t settling will increase. Basically inverse is increasing, so t settling will also increase. So from here also you can understand this, right? You can understand this. So it will be something like this. Now, like coming to the C option, obviously coming to the C option. So the C option, what it does is it adds a 0 over here. It adds a 0. So like we can obviously do it with normal calculation also, or without calculation also we can do, but we can do it with root locus also, or simple Routh Hurwitz also we can do. So let's do it with the both method. So we have been doing with the root locus, so let's again take help of root locus. So minus 1 minus 2 and plus 4, we have a 0, minus 1 minus 2 and minus 4, I have a 0. Okay, so again what will happen, this is a valid point. Again there will be some breakaway, there will be some breakups. Okay, but I don't support breakups, but still there like this world is like this, that there has to be some breakup, right? Else like, yeah, let's not go into that. So now, like, this is a valid point again because the number of poles and zeros are odd on the right hand side. So again I will extend this. Okay, so here I'll have virtual 0. So if I have a virtual 0 around here, this one will go from here and this one will go from here. Now we have a break in, so we are patching up now. So what is happening? So again, like, what will happen is, so this breakaway point will come here and break in here. Okay, my drawing is not that great, and this point will come here and break in here. Okay, so let me color the branches correctly. Okay, I made a mistake over here. This arrow should be correct only. The arrow F, yeah, I've corrected the arrows here. Yeah, arrow I should do correctly. and this one will be like this. Okay, so basically what do we see? Previously my root locus was shifting towards right, now it is shifting towards left. So my zeta omega n is reducing, zeta omega n is increasing, okay, because this is going shifting towards left. So like this portion is the underdamped portion, so zeta omega n is increasing, hence my T settling will reduce. So from the root locus itself you can understand that your T settling will reduce. But yeah, let's now further do this mathematically. So what will my characteristics equation will become? So my characteristics equation will become something like this. Here it is 2 into s plus 4 upon s plus 1 upon s plus 1. So it is 1 plus 2 s plus 4 upon s plus 1 into s plus 2 equals, okay, no, where did I go, equals to 0. So this will become s square plus 3s plus 2 plus 2s plus 4 equals to 0. So this one will become s square plus 5s plus 6 equals to 0. So from here my 2 zeta omega n is 2.5, sorry, it is 5, and zeta omega n is 2.5. okay, so zeta omega n is 2.5. now what will this become? Basically what will my settling time become? So settling time, T settling, 2% settling time, it has told us 2%, here 2%, so it is 4 tau. So simply 4 upon zeta omega n, 4 upon zeta omega n equals to 4 upon 2.5. okay, so it is, if I multiply this with 416 by 10, 1.6, 1.6, which is within our range, so like this, obviously reduces the settling time less than 2 seconds. So this is satisfying. So obviously only one will satisfy, we will choose this. So during the exam hall, how you solve this question? In the exam hall, what you will do is basically you will see that this is a lag compensator, this is an integrator, this is what I don't know, this is a derivative controller, proportional derivative. So this will reduce the settling time for sure. I know. Just to be double sure, I will check this if this actually reduces the settling time. I check this and I see that it makes the settling time 1.6. so this is the correct option. So I will choose this, okay, and then move on, because this is a MCQ type. Now if this was an MSQ type, obviously I have to check all of this, okay, if three or other three also reduces the settling time by 2 seconds, if the other three also reduces the settling time by 2 seconds, I have to check those also, okay. So yeah, that is how you basically analyze this question. So like simple answer you can give, PD controller, okay, fine, but let's analyze this with root locus. What is actually happening in the circuit? How is the settling time getting varied? Okay, so root locus is a very important tool to use, so don't forget how to plot the root locus. It is a very important thing to use, okay. So yeah, this is what I wanted to tell you. So everything is correct right here. I just wanted to cross check that I have done like the equations correct. Yeah, this is 2 3s, yeah, fine, 5s plus 6, yeah. Okay, I made a mistake. This should be 8, but it doesn't matter because we're talking about the zeta omega and this should be 8 actually. That is what I was thinking, that I must have made some mistake. So this will be 10, but it doesn't matter, okay, because like we are only interested in the coefficient of s, we are not interested in the constant term, okay, because that constant term tells about the natural frequency, not about the zeta, okay. Zeta omega is still dependent upon this. So yeah, sorry for that mistake. So yeah, let's start with this next question here. Like while reading this question, you might be a bit intimidated with the options and also with the question. So in these types of question, what you need to do is just start writing, just start the calculation, whatever they have told, just write those, okay. Then after going ahead a bit with the steps, then you will find some hint from the options, okay. So just again go back and forth from the options and your solution, with that. So like if you are not able to grasp the concept in the first round, first go, then you can mark for review and then come back to this in the second round. So that would be better, okay, if you are getting stuck, because don't waste too much time, because this will remain in your subconscious mind, and when you come back in the second round, it may so happen that some concept may get clicked in your mind. So yeah, that is how you solve this question. So this question at first may seem intimidating, so just start writing, just proceed whatever the question has told us to do. Okay, so like let's read the question. The system, this g of s is this, g of s equals to 900 by s plus 1 s into plus s plus 9. Okay, s plus 9, 900 by s into s plus 1 by s plus 9. Okay, so and its gain crossover frequency becomes same as its uncompensated phase crossover frequency. So like is to be compensated, this system is to be compensated. This is a open loop, because we're talking about the gain margin, phase margin, all these things. So gain margin and phase margin are only valid for OLTF. That's why this is a OLTF. From that I am able to understand they are talking about the OLTF. Okay, so as phase margin and gain margin are they're talking about phase one and gain margin, then this will be my g of s. From here we can understand this is my g of s, because many people get understand like what once they tell that this is g of s, once they tell that this is transfer function. How do we distinguish between the two, whether this is a g of s or this is a transfer function? So this is how we distinguish phase margin and gain margin. Okay, so now this is s plus s into s plus 1 by s plus 9. Now uncompensated phase crossover frequency and provides 45 degree phase margin. So it is to be compensated such that its gain crossover frequency becomes same as its uncompensated phase crossover frequency. So uncompensated phase crossover frequency. So can we find the uncompensated phase crossover frequency? What is phase crossover frequency? Phase crossover frequency is the frequency at which the phase of this OLTF is minus 180 degrees, where it crosses the negative real axis. So basically the angle of g omega at omega equals to omega pc will be minus 180 degrees. Okay, so this will be simply minus 90 degrees plus tan inverse omega plus not plus, it will be minus tan inverse omega by 9, and this will be equals to minus 180. So tan inverse omega plus tan inverse omega by 9 equals to 90. So which is equals to 90? I told you one formula, right? Tan inverse x plus tan inverse 1 by x is always equals to 90. Okay, or you can simply use that formula, tan inverse a plus tan inverse b is equals to tan inverse a plus b divided by 1 minus ab. Now 1 minus ab, as this is what this is 90 degrees is tan inverse infinity, so 1 minus ab has to be equals to 0. That will make it infinity. So 1 minus ab equals to 0, so a equals to 1 by b. Again, from there also you can understand one will be the reciprocal of the other. So I have forgotten to write that omega will be equals to omega pc. So let me write that here. This is omega pc, this is omega pc, this is omega pc, and this is also omega pc. Okay, so obviously my answer would be omega pc should be equals to 1 over omega pc by 9. So omega pc will be equal simply doing this correctly. What was this? Yeah, omega pc will be 3 itself, right? Omega pc will be 3 radians per second. Hence this has told that the gain crossover frequency after compensating becomes same as the phase crossover frequency. So that is one thing. Okay, fine. Now I start to read the options. So my omega gc after compensating, omega gc dash after compensating will be 3 radian per second. So what does it mean? Basically, the gain at that frequency of a compensator will be will be equals to what? So if I assume the gain gc of j omega at omega equals to omega gc equals to kc, okay, controller gain. Now, like, what will be my overall compensated system transfer function become? It will be overall g dash of s compensated will be the compensated transfer function into the g of s, okay, into the g of s. Now what will be the magnitude? The magnitude will be jg of omega gc of s into g of j omega, okay, which will be equals to, at omega equals to omega gc, the compensated gain crossover frequency gc dash should be equals to 1, because that is the definition of gain crossover frequency. The frequency at which the gain of the OLTF becomes 1. So we know the magnitude of this is kc, and the magnitude of this we have to find out. So kc into magnitude of this, what is this? It is this, right? 900 upon omega into under root omega square plus 1 omega gc square plus 1, and this is also omega gc actually, into under root omega gc square plus 81. Okay, so what is omega gc? Omega gc is 3. So this will be kc into 900 divided by 3 into 3 square, so under root 10 into under root 90 equals to what? Equals to 1. So kc will be simply equals to 900 1 by 3. So kc will be simply equals to 3 so this is under root 900, this one will be, just hold on a second, this will be under root 900 and under 900 3 by under root 900, I can say 3 by 9 into 100, which is 3 into 10, so which is 1 by 10. Okay, so what is 1 by 10? 1 by 10 is simply in dBs, it is minus 20 dBs. Basically log base 10, 1 by 10 is minus 20, like 20 is multiplied at the front, so it is minus 20 dBs. Now our controller gain at this frequency, okay, so remember this is kc at frequency, this omega gc should provide a attenuation of minus 20 dB. Now let's read the options again. So like it has told us which one we should use, which provides a phase margin of 45 degrees. Okay, now most cases when they are talking about the phase margin, like they are talking that the phase margin is increase. So phase margin will only increase with a lead compensator and not with a lag compensator, because lag compensator will provide additional phase lag, not lead. Okay, that is one important factor. So this one anyways gets cancelled out, and anyways we're seeing that a lag compensator that provides an attenuation of 20 dBs and a phase lag at 3 root 3 radian per second. No, we are talking about 3 radian per second. So which options have the 3 radian per second? Other options I can simply eliminate. So 3 radian per second is here and 3 radian per second is here. Okay, now here this is talking that a lead compensator that provides a amplification of 20 dBs. No, we are not providing an amplification. This is negative, right? This is negative. That means we're providing an attenuation. The amplitude is reducing. The amplitude is reducing. If the amplitude is reducing, that means we're providing an attenuation, not an amplification. So lead compensator was correct, but it is talking about amplification. No, I am not providing amplification. I'm providing what do you say? I'm providing attenuation. Okay, so this is also wrong. because lag compensator is anyways wrong and the frequency is also wrong. This is also wrong. Root 3 is anyways not here. So this is only the correct option. Okay. Here, a lag lead compensator that provides a attenuation of 20 dB and phase lead at 45 degrees at the frequency of 3 radian per second. So 3 radian per second is correct. Attenuation of 20 dB is correct. Okay, but let's just cross verify whether this is the this is also true or not, because they have also told us which provides a 45-degree phase margin after compensating. So obviously, initially finding the phase margin is difficult because you have to find the gain crossover frequency. This is a third order system, and for third order system, finding the gain crossover frequency is a bit difficult. There will be 3 roots and it will be difficult, right? So what you do is you can simply like here you could have done this also, that you could find the phase crossover frequency with this method. I will tell you another method. So what is the other method? Other method is simply this. I have already told you, I think, that you just take care of the imaginary part. So just convert this into g of j omega, g of j omega. Okay, so this will be j omega whole square. No, sorry, not whole square, sorry, this will be j omega into j omega plus 1 into j omega plus 9. Okay, so this will be 900 upon j omega into j omega whole square plus 10 j omega plus 9. Now again you multiply j omega, so this will become like j omega whole cube plus 10 j omega whole square plus 9 j omega. Okay, now what you do, obviously it will cross the minus 180 degree, so it will not have an imaginary component. Like it will cross this minus 180 degree, so it will not have any imaginary component, only real components will be present. So you will make the imaginary component 0 out of this. So if you make the imaginary component 0, so obviously, let me further simplify this. This will be 900 upon minus j omega cube minus 10 omega square and plus 9 j omega. Okay, omega cube, so this has to be 0, right? This part has to be 0, this has to be remain. So minus omega cube plus 9 omega has to be 0, so omega will be equals to 3, because I will reject the omega as a 0 solution, and omega equals to minus 3, because it has to be positive. So like this also you can find out in a faster manner. Okay, either you follow this or follow this, whatever you follow, you get to the final answer. That is more important. Okay, so yeah, now we got to the omega pc. This is the omega pc, phase crossover frequency. So we got to this. Like finding the omega gc is difficult, as I told, third order system. So like equating this with gain equals to 1 is difficult. So but they have told us that we know the phase gain crossover frequency now, because the gain crossover frequency, compensated gain crossover frequency, is equal to the uncompensated phase crossover frequency. So we know omega gc, just we have to find the phase at that, and we will be able to find the phase margin. So how to find the phase margin? So let's cross verify. So basically let's say that the controller angle j omega at this omega gc is some angle theta. Okay, let's say this is some angle theta. So theta positive means lead, theta negative means lag. Okay, now let me write the angle formula. So angle formula will be this only. Okay, this only, with just another angle will be added plus gc, because what will be my overall transfer function? Overall transfer function will be gc like this, right? G dash of s equals to gc of s into g of s. So g dash of j omega equals to gc of j omega, g of j omega. Now What will the angle? Angle will be simply the addition of these, right? If I take the angle of this overall, g of j omega, they are product. So if they are product, so angle will get added. If they are in product, so multiplication, I mean. So angle of gc of j omega plus angle of g of j omega. Okay, so let's find the angle at omega equals to omega gc. So angle of g dash of j omega at omega equals to omega gc. So this is, I have already assumed this as theta. So this will be theta plus g of j omega. So what is g of j omega? So g of j omega is angle of g of j omega is this, right? This portion. I have already written this. So I'll just copy this. Okay. And this is already like this is already minus 180 because omega pc equals to omega gc itself. So this is already minus 180. We know already this. Okay. So let me just still write it for better understanding. So basically this will be simply, now what is this, like what is my, they have told us that the phase margin is what, let me first write this, that my phase margin they have told us is plus 45, right? Plus 45. So if phase margin is plus 45, that means theta plus angle of g of p has to be this, angle of g of j omega gc. So not this, sorry, I'm talking wrong. 180 plus theta plus this, sorry, I should write 180 plus angle of g dash of j omega at omega equals to omega gc. Oh, I am really cramped of space. Let me write this above actually here or here, gc. And like let me do one thing, that let me color this one up to different color. Okay, so this is omega equals to omega gc. Now what will this become basically? So this will become my angle of g dash of j omega gc will become minus 135. So it has to be minus 135. This value has to be minus 135, right? So what is this value? This value is already minus 180, right? Because this is equated with this. So this I will replace omega pc, I will replace with gc, which is same because omega pc and gc are same for uncompensated and compensated system respectively, which is equals to 3 radian per second. So this is already equals to, if I put 3 over here, this will be equals to minus 180. So minus 180 will shift over here. So it will become plus 180 plus sorry, minus 135. Okay, because this is what I got from the phase margin relationship. Minus 135 should be equals to my theta. So theta will be plus 45. So it is providing some phase lead of 45 degrees at this particular frequency at omega equals to 3 radian per second. Again, we can cross verify that the D option is correct because lag lead compensator that provides attenuation of 20 dB, fine, and a phase lead of 45 degrees at frequency of 3 radian per second. So it provides a phase phase lead of 45 degrees at frequency of 3 radians per second. So yes, this is correct, right? It provides a phase lead of 45 degrees at 3 radians per second. So this question, or like the correct answer for this question is option D. So yeah, that from here we can solve this. So like let's first quickly, I want to say you one thing about lag lead and lead compensator. So what you can see with lag lead compensator, right? Lag lead compensator is like here, this is what, this is a lead lag compensator. So lead lag compensator can provide gain also, okay, and can also provide attenuation. Obviously not below this, but this is the highest gain, so it can provide attenuation also, it can provide gain also. at different frequencies. So that is the characteristics of a lag lead compensator or a lead lag compensator, because the gain and this gain, like it can provide gain and attenuation also. Up here also we can see, but in a simple lag compensator or lead compensator, it can either provide attenuation or gain. So like in the high frequency or low frequency, here we can see, okay, in the high frequency it is attenuating lag compensator, and in the high frequency the lead compensator is giving gain, okay, amplifying the signal at high frequency. Where is it, 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 where is it? Here it is amplifying the signal, okay. But there at high frequency it can like reduce also, increase also, depending on upon the pole zero locations, okay. So yeah, that is basically it for this question series lecture, and I will see you in the next lecture with a few more other questions, interesting assignment questions. So if you like this video, then do hit the like button, and I will see you in the next lecture. Thank you for watching.